Hi, everybody, and I wanted to keep going with chapter 2 here in this video. And we did start section 1 already. So I'm going to do a quick review of where we left off and then continue with that section. So chapter 2 starts us with an introduction to logic of compound statements. So section 1, we're focusing on logical form and logical equivalence. And equivalence really is another way to just say equal. So we started off with the idea of just kind of rewriting statements and using some new notation, maybe using P, Q, and R for different parts of a statement. And noticing that there is a common form to this particular argument. And it says, if P or Q, then R happens. So for instance, if the bell rings or the flag drops, then the race is over. So if one of those two things happen, then the last piece would also have to happen. Now, we can also reverse the order a bit, but have it still be a true statement. So the way to do that is to do it like this. If not R, then not P and not Q. So if the race is not over, then the bell has not rung and the flag has not dropped. That's the same basic core, right, meaning there, but we reversed the order. And to keep it the same, we did have to make a few changes here, right? We had to add in some nots and ands. This little symbol here, remember, means therefore as well. We can also use the conclusion idea here. So for instance, if I have a statement such as, if Jane is a math major or Jane is a computer science major, then Jane will take MAT 180. Well, if we know that Jane is in fact a computer science major, then we can go right to the conclusion, right? Because this statement has happened, so this must also have to happen. So therefore, Jane will take MAT 180. So a statement or a proposition is just a sentence that is either true or false, but not both. So this is a new idea here where, statements could be false, right? Sometimes you're trying to show something that something is not true. For instance, 2 plus 2 is 4. 2 plus 2 is 5. The first one is true, the second is false, but they're both statements. Something that is not a statement is something that does not have a clear outcome of true or false. So for instance, x squared plus 2 equals 11 is not a statement because it's true for some values and it's false for other values. So that would not be a statement. And then we started to get into notation. Now, there's different kinds of notation you can use depending on which language you're working in, for instance. We're going to be sticking with what is on the left here. So we're going to use this little squiggle here for not. We're going to use sort of like an upside down V for and then a regular V for or. Again, there are other notations. So some textbooks have used this for not. If you're programming in Java, C, or C++, for instance, then not is an exclamation point and would be a double ampersand, and then or would be 2 vertical lines. So again, there's different abbreviations depending on the language you're using. For our class, we're going to be using more of the mathematical notation, and these will be our shortcuts. And then I'm also going to be using that abbreviation of therefore, which is that 3 dot triangle too. So for instance, something like this means not P. Something like this means P and Q. There are order of operations here. So not comes before and or statements. And or statements are considered equivalent. So if you're going to have multiple of them, you do want to have parentheses to show what you should be doing first. And then here we had 2 statements that are used a lot, but are not quite clear really what they mean. So when you have a logic statement that has P but Q, so something but something, you're really saying P and Q are occurring. Neither P nor Q, another way to say that would be not P and not Q. So both of them are not occurring. And we left off with this example here, just to start getting used to using this shorthand notation. So let H be the phrase, it is hot, and let S be the phrase, it is sunny. It is not hot, but it is sunny. Again, but is another way to really think of as and. So we can write this as not H, right? Not hot, and sunny, S for sunny. If I want to say something like it is neither hot nor sunny, I'm really saying that it's not hot and it's not sunny. So we're able to write that abbreviation this way. All right, let's do another example here. And I'm just going to go to a new page. So another good example that we use a lot with this and or notation are inequalities. So they use and or a lot as well. So for instance, if I write something like x is less than or equal to a, what this really means is that x is less than a or x is equal to a, right? When I use a less than or equal to sign, we actually have two ideas there. We could be equal to the value or we could be less than. And if I have a double-sided inequality like this, then we're really saying that a is less than or equal to x, and x is less than or equal to b. So notice the difference here. This first statement, we had an or, right? Because you could be one or the other, and it would still be fine, still be true. Here, we have an and statement, right? X has to be in between both of those values. So we need both that x is greater than or equal to a, and also that it is less than or equal to b. So let's let P symbolize that 0 is less than x, and Q symbolize that x is less than 3. And we'll let R symbolize x is equal to 3. Let's say I want to take the inequality x is less than or equal to 3, and I want to write it using our new shorthand notation, using P, Q, R, the or symbol, the and, the not, whatever I need to do here. So x is less than or equal to 3 means that x is less than 3 or x is equal to 3. So if I look here, Q relates to x is less than 3, and R relates to x is equal to 3. So what we're saying here is that this is Q, this is R, and I need the or symbol. So the or symbol looks like that V in between. Let's try another one. 0 is between, x is between 0 and 3. So what we're saying here really is that 0 is less than x, and also x is less than 3. So I need both of these things to be true. So 0 is less than x is represented by P, x is less than 3 is represented by Q, and I have an and statement here. So it's the upside down V. Actually, let me switch this one. Let's mix it up a little bit. Let's do one more. So 0 is less than x is less than or equal to 3. So what are we saying here? We're saying that 0 is less than x and x is less than or equal to 3. Well, 0 is less than x is pretty straightforward. I already have that is symbolized as P. X is less than or equal to 3 is more difficult though. I did that back here in A, and that symbol is this right here, right? It's actually two parts. It's x is less than 3 or x is equal to 3. Two things are occurring there. So what we have here is not just a simple statement, but you actually have that it is Q or R, right? And that's from part A. Now I want to put an and symbol in between here, so I can do that. But you do want parentheses around this group because this really goes together, right? This whole thing means x is less than or equal to 3. So I need parentheses around this to kind of show that this is together. And then I need this and this. So when we write these statements, When we start changing over to this new notation, we do want to be really careful about how we are writing that and just take our time. All right, the next thing I want to talk to you guys about are called truth values and truth tables. All right, when I say a truth value, I just mean, is it true or is it false? So truth value is either going to be true or false, right? Again, we're not talking about any ambiguous statements here. And then we have another definition of a statement form, also called propositional form. And this is an expression made up of statement variables so for instance, you know, P, Q, R, like we've been using, and logical connectives. Example, the not symbol and an or. That becomes a statement when actual statements are substituted for component variables. So what's kind of happening here, let's use a different color for a second, is that P, Q, and R are statement variables and allow us to talk generally. So you're going to see that we have a lot of common forms in logic that we use. I kind of showed you one already of the idea of, you know, P or Q then R, right? So there's kind of some common forms that we use. So P, Q, and R are like variables. So you can substitute in any other statements that you're trying to use, like actual English words, right? But those general statements still kind of hold. So we think of them like variables as placeholders for what the statement would actually be, let's say in English or in math. Or in programming or whatever it is. Also, P and not P have opposite truth values. So for instance, you know, if P is true, then not P is false, right? And vice versa. So remember, statements are either true or false. So if P happens to be true, then not P would have to be false. It would be the opposite of it. And we can write this like this. So if P is true, not P would be false. Or if P was false, then not P would be true. And this right here is actually called a truth table. It's a way for us to kind of organize what statements are true, what statements are false, and kind of follow the logic along the way. So if P and Q is true, or it is true, oops, let me not abbreviate here, if and only if, and I'm going to start abbreviating that. So if and only if, we tend to abbreviate as IFF to save some writing. Both P and Q are true. So if P is true and Q is true, then P and Q would also be true, right? Because both parts would have to be the same. But if one of them is false, it would make the and statement false as well. This is actually called, by the way, a conjunction. Having that and piece there. So for instance, I'm gonna do a truth table. And what a truth table does is it goes through all combinations that could occur. So for instance, P could be true and Q could also be true. P could be true, but Q could be false. P could be false and Q could be true, or they could both be false, right? Those are the four things that could happen with two statements, right? Again, I'm just talking generally here. I'm not telling you what the statements are. I'm just saying in general, if P or Q are any statements, these are the four possible things that could happen. So, and is true only if all parts are true. So since both parts are true here, this would also be true. One part is false, so this has to be false. One part is false, so this has to be false. Both parts are false, so this is also false. So when we do truth tables, if you have a conjunction, if you're trying to do an and statement, if you want it to be true, then both of the original parts have to also be true. All right, let's do an or statement. So this is true if either E is true or Q is true, or they're both true. And again, this is called a disjunction. So let me do a truth table here. So I have P and Q. And then I'm trying to figure out, well, what happens with P or Q? So again, P could be true and Q could be true. P could be true, but Q could be false. P could be false and Q could be true, or they both could be false. So what happens here for an or statement is the outcome is true as long as one of them at least is true. So here, if they're both true, it's still true. Here, as long as one of them is true, it's true. As long as one of them is true, it's true. And the last case, because both of them are false, then this would also be false. So for an or statement, you need at least one of the statements to be true for the whole disjunction to also true. All right, let's do a couple of examples here with larger truth tables. All right, so we're going to construct a truth table for P or Q and not P and Q. So what you want to do here first when you're doing a larger truth table like this is just look at the individual statements. So I have two variables here, P and Q. So that's how I'm going to start. And again, I'm going to think about all the combinations here. I'm just going to give myself a little bit of room so they can both be true. P could be true, Q could be false. P could be false, Q could be true, or they could both be false. So when you're starting with the truth table, you're going to look at all your variables, however many variables you have, individual ones, right? Unique ones, P and Q, you start with that and think about all possible combinations. And then you're going to start breaking it down and you want to do it like pieces, little pieces at a time. So particularly things in parentheses are good to do in the next section. So I'm going to do P or Q here. And you don't have to write the parentheses, but you can, whatever is easier. I'm going to figure out what would happen for this piece. So if it's an or statement, remember, as long as one of them is true, then the overall answer is true. I'm also going to do this next piece here. So again, I'm not going to do everything at the same time. I'm not going to do the not yet. I'm just going to do the inside P and Q. And again, you don't really need parentheses, but I'm just going to keep it in just to make it a little bit easier to see. And go back to here and think about, well, what happens? For P and Q to be true, they both have to be true. So this first part is true, but the rest are going to be false. Now I'm going to bring in the not. And the not is going to switch over all the signs in this group, right? So when we have a negation here, everything is going to flip. So if it was true, it becomes false. If it's false, it becomes true. And I don't need to look at everything at once. That negation is only on this part. So I'm going to negate just that column. So true becomes false, false becomes true. Now, I usually put vertical lines in just to kind of separate my beginning, middle, and end work, but it really doesn't matter where you put them. If you want to put them between everything, I personally don't care. Whatever keeps you organized. And now you can see I have all the parts done, but I do need to put everything together, right? I have this big combination to put everything together with the and symbol. So I'm going to finally get ready and do that last piece. Now, when I'm doing this, I'm not comparing everything. I'm looking at P or Q. So I'm looking at this group. And then I'm looking at the not P and Q, which is this group. And then I want to know what's the outcome when I have an and symbol. So remember, for and symbols, for it to be true, both parts have to be true. So if I look here, this one's true, this one's false, but not both true. So this outcome is false. Here, true and true, so that looks good. True and true, that looks good. And then this one, I have a false, so this must also be false. And that is the end of our truth table. So what does this kind of do for us? It basically shows you what the outcome is going to be for the statements based on if they are initially true or false. So for instance, it doesn't matter what the statements are, whatever my statements are. If my P is true and my Q is false, or my P is false and my Q is true, then this statement here is always going to be true. So you can kind of generalize if you know the false and true nature of the original statements, we can combine them in different ways and already know the outcome of if they're going to be false or true without having to even know the exact statements. So these are our truth tables here. All right, let's do one more example. All right, so same thing. We're going to construct a truth table, and we're going to do for P and Q or not R. So for this truth table, notice that we have three distinct variables. I have P, Q, and I'm bringing in an R. And you can use any letters here. P, Q, R tend to be the most common, but you see M's and N's a lot too, S's, and so on. So any letter is fine for the variables here. But what I'm going to do is I'm going to start with my variables. So I have three variables. So I'm going to make three columns. All right, I'm just gonna have enough room. Now, it gets a lot harder every time you add in a variable because there's more combinations. Before we only had 4 different things that could happen, but with 3 variables, there's a lot more. There's a lot of different things that can happen. So I'm gonna show you all the different combinations. So the first is that all 3 could be true, right? The second thing is that 2 could be true, right? So maybe P and Q are the true ones, but R is false. Or it could be that P and R are true and Q is false. We could also have 2 that the first is true and then the other 2 are both false. So these are all the things that can happen with P being true. So I'm just kind of keeping a little bit small for a second. So if P is true, then it could happen that the other two are also true, that only one of them is true, or that the other two are both false. Now it could also happen that P could be false. So it can happen that, P is false, and maybe the other two are true. P is false. Q is true, but R is false. P is false. Q is also false, and R is true, or all three could be false. So those are the combinations. There's 8 combinations, which hopefully makes sense, because if you think about it, each variable has 2 outcomes, right? True or false, and there's 3 variables. 2 to the 3rd power is 8. So that's where it comes from. But it's good to just know the pattern. So you don't have to think about it every single time to get all the combinations. Just start rewriting the patterns. So when I only have 2 variables, the pattern I always use is true, true, false, false. And then this one alternates true, false, true, false. That gives you all the patterns for 2 variables. Here, if you have 3 variables, the pattern that I use for P, or the first variable, I do 4 trues, 4 falses. Then I go by 2s. 2 true, 2 false, 2 true, 2 false, and then I alternate. And by doing that, you do get all 8 combinations. So I start with that first. Now I start to break it apart. So I do see something in parentheses here. So I'm going to go ahead and do P and Q. And again, just make sure you focus on the right columns. I'm only looking at P and Q here. So I'm looking at the first 2 columns. And if they're both true, this is an and statement, then the outcome would also be true here. So this one would be true. Again, both true. Now my Q is false. So this will be false. My Q is false. My P is false. My P is false. False. I don't need to rewrite R because I have R, but I do want to do out what not R is. You don't want to do too much in your head. You want to write each step in the table. So the not is going to switch all of these over. So true becomes false, false becomes true. Excuse me, all the way down the line. And now those are all the main components. I'm going to put it together in an or statement next. Now for the or statements, just be careful. If it's an or, it means that as long as one of the parts is true, then the answer would be true, right? Now you don't have to always highlight. This one doesn't have too much going on, but if it helps you, you're looking at this column and this column. And then don't forget you're doing an or statement here. All right, so let's go down, and I'm just going to change colors here to make it a little bit easier. So as long as one of them is true, again, because it's or, the answer will be true. So true. Here I have a true. Here they're both false, so it will be false. Here I have a true. Here they're both false, so it's false. Here I have a true. Both false. And then finally a true. Excuse me. So that is how we do our truth table. So we go one little piece at a time, make sure you have all the variable combinations included, and then just be really careful with and versus or. They have different outcomes, right? So for and to be true, all parts have to be true. For or to be true, you just need one of them to be true. So that's going to change the outcome here. And again, what this does is it gives us a general understanding of what happens for different kinds of statements. For instance, if I know all 3 of my statements are true, then I know the outcome of this combination is also true. Doesn't even matter what they are. They could be statements such as, I don't know, 2 + 2 is 4, 1 + 3 is 4, and 4 + 5 is 9, right? Those are 3 true statements. So whatever they are, however they are true, I know that this combination is always true, no matter what they are.